This talk is going to be on one important facet of unsupervised learning. We'll talk about a couple of things, little bit of history about this, like when one hears about unsupervised learning or clustering, the name, the algorithm, which is often one's first choice. In fact, one of the most cited papers in pattern recognition machine learning is Professor Anil Jain's paper, 50 years beyond k-means. Okay, and so k-means has become such a de facto standard that one often applies it as a first cut algorithm. And the format, the way we know the algorithm today is due to this gentleman, McQueen. And yeah, this is interesting. What is the first thing that pops up into your head when you hear the term McQueen? Disney cars. Yeah, so this is Lightning McQueen. And there's actually a relationship. The relationship is interesting. The relationship essentially is that this algorithm is actually blindingly fast. Okay, so it's actually blindingly fast. And in fact, it can be done in linear time also. We'll talk about these things. And this algorithm has been discovered and rediscovered over the ages, as you can see. And people, especially those in electrical engineering, in those who are working in audio, they call it vector quantization or VQ. It's called clustering, bunching, grouping. Yeah, people call it names. It's a very old algorithm. It's more than it's about half a century old. It's old, but it's often still one's first choice. Well, learning comes in many flavors. There is supervised learning. Yeah, we at least at IIT Delhi think that whatever we are teaching students, that is more of supervised learning. However, our students believe that whatever they are learning is actually unsupervised learning, right? So our role is completely compromised in that case. There's also one flavor of learning, which is, well, in supervised learning, the idea typically is that there is often a training set. There's a training set, and we also have, so in addition to, let's say, n points in a d-dimensional space, we are also given the ground truth. So that ground truth could be something like either the class information, it could be the class information, or it could be things like a regression value. Okay, in unsupervised learning, that ground truth is not there. We are trying to make sense of some groups, some clusters in the data itself, some intrinsic properties. Reinforcement learning is interesting. Reinforcement learning is learning with a critic, okay, as opposed to learning with a supervisor. Now, what is a critic? A critic also could be stochastic. A critic just tells us whether we are right or wrong. A critic just gives a yes or a no answer. And a critic could be stochastic, right? A critic could be correct at some point in time, could be wrong at another point in time. Can you give a good example of reinforcement learning in day-to-day life? It's actually come from the domain of psychology. One of the best examples of reinforcement learning is learning how to ride a bicycle. And in fact, it said one of the basic premises behind reinforcement learning is that normally examples of reinforcement learning are examples of lifelong learning. So once you learn it, you never tend to forget it. It's like riding a bicycle. That is one of the best examples of reinforcement learning, because here, learning to ride a bicycle, the reinforcement signal comes from within the system itself. That intrinsic sense of balance. If I'm falling over this side, I'll try to adjust my handlebars in such a way, or adjust my body in such a way that so the reinforcement signal starts coming from the system itself. Okay, so this is one of the best examples of reinforcement learning, learning how to ride a bicycle. Another example is, which is not completely reinforcement learning, but it's actually learning how to swim. Swimming is actually a combination of supervised plus reinforcement learning. See, the sense of balance and the sense of flotation just doesn't come otherwise. That part is purely reinforcement learning. Then there's, of course, there are some other flavors like semi-supervised learning, in which the ground truth is given, but then it's not given for all data points. So there are lots of these flavors, and there are lots of practical applications of all of this. Key means this particular algorithm is one of, and it's an unsupervised method, and k-means normally comes in two flavors, one of which is popular in terms of textbooks. We'll talk about a couple of textbooks in this field, and one of them has k as a parameter, which is why the algorithm is called k-means. And in the other one, it may have something like a distance threshold as a parameter. Okay. Now, in terms of getting groups, there could be crisp decision boundaries. For instance, grading. Well, everybody with more than 80% may get a A grade. Then let's say between 75 and 80, you'll get a neg, or so on and so forth, A minus. So there could be crisp decision boundaries. Okay. And in addition to crisp decision boundaries, there could be cases where the decision boundaries need not be crisp. Then another example is, well, the division of states on a linguistic basis. I'm talking about controversial matters. We'll take up this example also. Then getting the region of interest from a fingerprint image. Then some concepts themselves could be fuzzy. Let's say signal noise separation, or the concept of well-built. Typically a person, the concept of a well-built person is, well, the height should be reasonable and the weight should be, the weight might be a bit unreasonable also, like in my case. Okay, so some concepts could be fuzzy as well, while some concepts could be crisp. Okay, let us start with uh, algorithms, the basic concept of algorithms. Who is this gentleman? Well, this gentleman is actually Mr. Algorithm. This is Al-Khwarizmi, and he was, how do we know him? We know him as, see, one of his treatises is something called Al-Jabr, and which was anglicized to get the term algebra. And in fact, the term algorithm is actually a anglicization of his name, Al-Khwarizmi. And in fact, he's responsible for many things in mathematics and computer science. The basic idea of the Indo-Arabic numerals, which sort of flowed from the east to the west. See, before that, Europe used only Roman numerals, which, as all of us know, all of us still get nightmares about using Roman numbers. Okay, and Al-Khwarizmi was the first to actually introduce the what are called the Indo-Arabic numerals. He introduced them to the West. And in fact, things like a quadratic equation is the highest degree equation which was solved in closed form for a general case. So he gave a method to solve quadratic equations, which we take for granted. Then things that we take for granted, if we have something on the left-hand side of the equation, we take it on the right-hand side, it will change its sign. So plus becomes minus. And if something is there in the numerator, take it to the other side, it will come to the denominator. These rules are his. And from the point of view of computer science, he also proposed something that is very important. That is, if we need to solve a particular problem, there should be a finite number of steps. So this essentially is what his importance is to basic algorithms. And we started off with a slight filmy touch. Do you remember that? We took an example of Lightning McQueen, okay, that Disney cars example. We'll give it another filmy touch. I like to classify algorithms into three categories. Okay, to give it a filmy touch, I call them the good, the bad, and the ugly. Okay, the good are algorithms with a polynomial time complexity. That is, if n is the size of the input, and if the number of steps that is taken is of the order of the size of the input to a polynomial power, to the power of a constant, they are good algorithms. So anything like all sorting algorithms are good. The DFT, which is order n square, that's good. FFT is order n log n, that can be bounded by order n square, that's good. The bad algorithms, there are algorithms which have exponential time complexity. That is, the number of steps is a constant to the power, the size of the input. Some of you, well, all of you would know from Boolean mathematics that if I've got n Boolean variables, how many minterms would I have? We'd have 2 to the power n. And if I need to construct a Boolean function, I'll need to take n choose k out of them. And that itself should give us the shivers, because so the number of functions is basically 2 to the power 2 to the power n. That's horrible. That's bad. And it is in this class that we consider two of these. We consider the class of NP complete problems, wherein at least there is a hope that if I solve one of these problems, if some genius comes up with an algorithm to solve one of them in polynomial time, then the other problems in this set I can convert to this particular problem and end up with a polynomial time solution. These are NP complete. NP hard are was, even if a genius comes up with a no guarantee that the others can be solved in polynomial time. Well, there are lots of these examples. I gave an example of Boolean function design. Then there's, of course, the traveling salesperson problem, so on and so forth. Well, there's something worse. This is what I call the ugly category. These are typically numerical algorithms which actually converge to the correct solution in that is the key point. Okay, they'll converge with probability 1, but will typically take infinite time to do so, or there'll be no time bounds. That's bad, or rather that's ugly. And unfortunately, typically machine learning algorithms, most of them fall either into the ugly category or the bad category. We are actually typically looking at one algorithm which can fall into the good category. Okay, let's go ahead. So let's try to give a slight bit of a mathematical description of the problem. I've got capital N points. So these points could be vectors. They could be represented as column vectors in, let's say, d-dimensional space. So these points are where capital N is a pretty large number. These are to be grouped into capital K clusters. Okay. All right. Just a little point on this particular interface. Please don't just raise your hand, just speak, just unmute your microphone and speak. I've got a very old Baba Adam ke zamane ka computer on which I'm running Linux. And okay, so Vasantala Sai Teja, Dr. Sai Teja, can you just speak out into your microphone? I may not be able to see.
Yeah, in today's session, you can unmute yourself. And when you unmute, please also don't forget to mute your mics after the question. So please unmute and you can ask questions.
Or point out errors, as the case may be. Yeah, Dr. Saiteja, please go ahead.
Or you can write in the chat thread, please.
Okay, I'll try to get the chat box up. Let me see if I can get that interface up. Should be possible. Yeah, there's something in the chat box. Feedback is also reinforcement learning. Yes. That is in fact a rather nice example. And electrical engineers talk about feedback, right? So as an outcome of this lecture, please do not give too much of positive feedback. Why? Positive feedback, as anybody in electrical engineering knows, causes oscillations, right? Oscillators are designed with positive signal feedback. On the other hand, negative feedback, as we know, as all control theorists know, that results in stability of the system. Okay, so yeah, is there any question? Okay, if there's none, then I guess I can go ahead. Okay, these are capital N points. These need to be grouped into capital K clusters. And for each cluster, there has to be a prototype vector. For instance, it could be the center. We'll talk about these sort of things. And we want to also put a sort of a mathematical optimization problem on top of this. We might want the aim to be 1 such that the sum of squared distances of each data point to its closest prototype indicator or indicator vector mu j is a minimum. That's a pretty viable and a reasonable goal. And in vector quantization, mu j, these prototype vectors or prototype points, these are called codebook vectors. And we'll talk about an objective function or a distortion measure that we'll try to optimize. But let's take a little example first. Let's look at this animation. Well, we can see that there are 3 clusters, okay? But that information is not given to us. What we'd like to do after running this algorithm is that we'd like to color these points. We'd like to color these points, let's say red, blue, and green. And after coloring them, we'd like to take a rope or a lasso and haul all the green points together, haul all the blue points together, and haul all the red points together. And after that, we want to also have one prototype which sort of characterizes that particular group. Okay, so it's like let's say the division of states on a linguistic basis. So if we have one long feature vector, let's say, which is let's say one of India's 21 or 22 national, not really national, but then, yeah, officially recognized languages. So if we have this particular vector, and in addition, we put the latitude and longitude coordinates of every person. So we have one feature vector, a 24-dimensional feature vector, which characterizes a linguistic and geographical distribution of a particular person. Now, for instance, let's look at the boundary, that the traditionally disputed boundary between Maharashtra and Karnataka. So typically you'll find people in northern Karnataka speaking both languages, speaking Marathi as well as speaking Kannada. You'd find people in southern Maharashtra also speaking both languages. So there, please remember that the decision boundary, although it has to be crisp, it has to be crisp in this case because we want this decision boundary for a state to be crisp in that sense. But then we are bound to incur an error, because by drawing this decision boundary, there would be Kannada speaking Kannadigas, so to say, in southern Maharashtra and Maharashtrians in northern Karnataka. But then we want to minimize that. So there's obviously an optimization problem at hand. Plus, after a regrouping, after a grouping of people on the basis of one's mother tongue, after grouping them into linguistic components or states, one wants to have one prototype vector, which could be the state capital. Okay, so there could be a non-mathematical reason for designating a particular city as a state capital, but we want to get a sort of a mathematical description. Okay, so this sort of, look at this sort of a function. Here in this function, Rij is a binary indicator variable. It's a 0-1 variable, wherein Rij is said to be 0 if point number I belongs to group number J and is 0 otherwise. And here we are taking a norm, take any norm, take a Euclidean norm or whatever norm. It's essentially the distance of the ith point from the jth prototype vector. And overall, this has to be minimized. Okay, so I can pose this optimization problem as: find me the parameters Rij and μj in such a way that this j, I should, of course, to be mathematically precise, I should write j as a function of Rij and μj. So I want to get a minimization of this particular function. Okay, this is what I have just described in words. Now, one way to solve this is in two phases. This is also called the expectation maximization framework, and this is something that we'll also look at soon, pretty soon. Now, well, you might think, well, why is this weird young person weird young instructor trying to tell me that I should do it in two phases? Why can't I do it all at once? Well, even a beginner control theorist would know that if I've got a linear set of equations, which can be described by Ax equal to B, okay, and let's assume that matrix A is full ranked, okay, and it is perfectly invertible. So X should be A inverse B. Now, even in this case, even if I try to do it all at once, a control theorist would shiver. Why? Because if he or she remembers that if this vector X could actually, if this is actually pretty large, so A would typically be a K cross K matrix. And we know that trying to invert a K cross K matrix where K is pretty large is often numerically pretty bad. It's often infeasible. So what people do is typically one divides the set of parameters into two sets. One makes a guess for half of them and then tries to optimize and find out the value of the remaining half. And then in the next phase, switch the roles of the two, fix the second set, and try to optimize and find the first set. This essentially encompasses the philosophy of expectation maximization. So one way to do this is to choose the K initial cluster centers. They could be done in any way. It could be done in an arbitrary way. They could be perfectly random, or we could choose the first K or whatever way possible. Then what we have done is we have fixed the first set of variables. Now we find the binary assignment values. So this is called the expectation phase. And in the second phase, we will keep the Rij's fixed and try to optimize over mu j. This is called the maximization phase, and we repeat till either convergence or a fixed maximum number of iterations. One very nice thing about this formulation is that each step is provably convergent. That is, if we look at every step, it is involved with either a decreasing or at least a non-increasing case of the optimization function. Why? Let's look at the expectation step. One very simple way to do it is for every point xi, assign it to its closest cluster centroid. Okay, so by construction, we can get a minimization of this particular step. That's nice enough. Good for us engineers, right? We don't have to think too much about it. And what will be the time complexity? How many points are there? There are n points, and there are these k prototype vectors. So for every one of these n points, we check for a distance from the k prototype vectors. So this has time complexity order n into k, and k is typically a constant. So this is linear time again. And the second step is the minimization step. How would we do this minimization? Okay, this is easy enough. This is quadratic in mu j. So what we do is we typically take a partial derivative with respect to mu j, set it equal to 0. Here, there is only one particular term which involves j. That's it. The others involve j minus 1 or j plus 1, so on and so forth. So they are constants with respect to the jth term. So we just reorganize these terms, and what we get at the outcome is this particular formula. Let's look at this closely. What is the denominator? The denominator is the sum of all the Rij's. Now, do we remember what the Rij's were? They were the binary indicator variables. They are 1 if point number I belongs to cluster J and is 0 otherwise. So what is the denominator? The denominator is simply the number of points in a particular cluster. That's it. What is the numerator? The numerator, again, because of the 0, 1 nature, is essentially the sum of all of these points in that particular cluster. So what is this? This is the mean, okay, or the expected value. We'll talk about the relation between the mean and the expected value. I've used it a bit carelessly, but then yes, there is a relationship. So this essentially is the mean. So this is the reason why this particular algorithm is called the k-means algorithm. We have some arbitrary initialization, apply the expectation step, and the function at least is a non-increasing function. And in the second one, we recompute the cluster centers. Okay, how much time does it take to compute a mean? It's always linear time, right? We add number of points and divide by the total number of points. So this second step is also linear in time complexity. And this function will definitely converge. It is provably convergent. However, it might converge to a local optimum. And that is sometimes a bit of a worry, but it will converge. It's guaranteed. And we repeat these till either there is no change in assignment or a certain maximum number of iterations is exceeded. Good. Let's illustrate it. So I've taken this example directly from Christopher Bishop's textbook. So in this case, what does intuition tell us? Intuition tells us that there are two clusters. So we start k equal to 2. That's actually a good question. How do we know what capital K is? So in this case, we've taken an arbitrary initialization of the prototype vectors. What is the first step? We assign every point to its closest cluster prototype. What is an application of k-means? A natural application to images is segmentation. We can use this for image segmentation. Okay. And towards the end of my talk, I'll talk about one of the most practical uses of an online variant of the k-means algorithm and the expectation maximization, which is the Stauffer and Grimson background estimation algorithm. An algorithm to automatically estimate the background in given a video or a set of video frames. I'll try to illustrate that. Okay, so something exciting coming up again. Okay, so in this case, what is the first step? The first step, assign every point to its closest cluster centroid or prototype. So in this case, we are basically coloring points according to whichever prototype it's closest to. So the points which are closer to the blue one, we color them blue. The points which are closer to the red one, we color them red. And then we recompute the cluster centroids. Next time, again, we follow that, assign every point to its closest prototype vector, and again, recompute the centroid. And one of the things that we find is after a while, these points do not move. So it has converged. It is provably convergent. However, there is no proof. There's nothing to tell us that these would be global optima. Why? This function need not be convex. Okay, in this case, for instance, we involve the 0, 1 binary indicator vector. It's obviously non-convex, right? So, okay, some points. Yes, this could converge to a local minimum. Initialization could be random. What are the time complexities? And we could run an outer loop for every possible initialization. Well, that complexity could get pretty large. And we could also have an outer loop which runs it for a couple of sample values of k, because typically nobody tells us k beforehand. There's also an alternate formulation that works with a distance threshold. It can be used in a bioinformatics application, for instance. There are things like so typically most what's called rational drug design, people don't really follow a wet chemical engineering process. It's very costly. Enzymes are very costly, and second, some of these compounds, chemicals, can also be very dangerous. So what people do is one takes recourse to machine learning techniques there. One tries to find what are called active sites. Active sites are typically those sites where the reaction actually takes place, like ligand binding. Okay, so a structure determines functionality. So people try to design a new drug by using structures of existing drugs. Okay, so one tries to look for tight clusters. These are typically active sites. So in this case, an online variant of k-means can actually be used. An online variant of k-means can be used. That is, for instance, if we have things like, what are the basic building blocks of proteins? They're amino acids, right? So take an amino acid residue. It forms its own cluster. Take the second one. If it lies within a distance threshold, for instance, 3.6 angstroms is one threshold which has a good amount of biological significance. So if it is within 3.6 angstroms, call it a part of the same cluster and recompute the cluster centroid. Take the third amino acid residue. If it is within 3.6 angstroms, then it is take that to be a part of the same cluster. Otherwise, take it outside as the second cluster, and so on and so forth. So in this case, this is sort of complementary. So in this case, the distance threshold is the parameter which influences. And plus, there's, of course, one could have an outer loop, right? Because it basically depends on what order these points have been given to the system. There are obvious limitations. For instance, if there are two classes and data is organized in concentric circles, okay, then both the classes have the same mean. So they cannot separate them. Okay, so k-means will not work for this particular case. Well, there are solutions. There are algorithms like density-based scanning, DB-scan, which works for this case. Or if you're more familiar with machine learning, things like the kernel trick. Okay, the kernel trick will take your data onto higher dimensions, and then what we do is we hope and pray that we get a linear decision boundary on that higher dimension. There are lots of ways to handle this. Plus, there are so one generalization of the k-means algorithm is one which involves a probabilistic or fuzzy assignment of these variables, okay, of Rij, so on and so forth. Okay, now we'll switch gears and go on to the second part of the talk, which is essentially a mixture of Gaussians. And in taking a mixture of Gaussians, we'd like to look at curve fitting. Now, one of the more important things here, or interesting things here, is that let's remember a couple of basic points. First is, almost any parameterized curve can be fitted to a bunch of points with an associated error cost. Okay, for instance, given points in 2D, if we have a cigar-shaped distribution of points, then a linear fit can be a very good example, right? On the other hand, if data is uniformly distributed in 2D, we can still have a line. We can still have a line which fits the data, but it will be a bad fit. Why? Because the average distance, the average perpendicular distance of any point from that best fitted line is quite a lot. Okay. The second thing here is that a Gaussian is computationally nice. Why is it computationally nice? It's computationally nice because it is completely characterized by two parameters. What are the two parameters? The mean vector and the covariance matrix. That's it. Okay, so if we are given any particular probability mass function, so any hump or bump, if we have any hump or bump in the probability mass function, we can fit one Gaussian to it. Okay, and a constant region, how do we model that? We fit one Gaussian. Whenever the influence of the first Gaussian is coming down, we fit another Gaussian there. So we have a slowly varying curve out here. So that can characterize any constant region. Okay, we have somebody has raised a hand, Dr. Soham Kapse. Yeah, please unmute your microphone and speak. Please speak. Please unmute your microphone and speak, because I have a very small screen out here and I cannot possibly see every. Well, I see a couple of chat messages here by Dr. B. Hariharan. Reinforcement is only reward based learning. That's an interesting point. It's actually a big philosophical point here as well. Then how can machine learning be implemented in chatbot? There are lots of ways. In fact, one of the classic examples of machine learning is in a email spam detector. It's typically a Bayesian. It's typically a Bayesian, a naive based learner. How do you characterize a mail as spam or not spam? In fact, most of us have machine learning based spam filters that are associated in all of our emails. Yeah, I cannot see these. So please, Dr. Soham Kapse, I saw this name here popping up on my screen. So please unmute your microphones and speak, because getting to see all chats and all of these is not very easy on my sort of interface. Hmm? Okay, so that might have been by mistake. Okay, so suppose our model is one Gaussian. Then if I'm given this following probability mass function, I can still fit a Gaussian to it. But then, as you can see, this is a bad fit. Why is this a bad fit? One Gaussian, that is because in a Gaussian, the mean, median, and mode coincide. So the point across which the number of samples should have been the largest actually has no representation at all. So this is a bad fit. On the other hand, fitting two Gaussians may be a better fit. What is this? This is 2G. From 2G, where do we go? 3G. Okay, so three Gaussians. So if we have a sum of three Gaussians, is this a good strategy? Well, I think you can realize that this may actually not be a very good strategy. Why? Because there's actually a speed limit in probability. What is the speed limit in probability? The speed limit in probability is 1. We are not going to exceed 1 as a sum of probabilities. Otherwise, the mathematics police is going to come and catch us. So we have a problem. The problem is probability. The solution is also, because most of us are engineers, we'd like to get out of this. So one way is, instead of simply adding the Gaussians, why don't we take a linear combination? Okay, or a probability weighted sum. So the idea here is we model the probability mass function as a linear combination of existing Gaussians. Okay, see, this is still Jugaad, what is called in the chaste vernacular of the region. So next time, please don't call it Jugaad, call it an engineering approximation. Okay, so this engineering, so we make an engineering model. However, we'll also have to justify this. Okay, that's what we are going to do in the next couple of slides. So the idea is we finally need to put the expression as a linear combination of our Gaussians. How? So we need some stamp of approval from mathematicians, and mathematicians, what we are looking for is the Bayes rule, okay, which is essentially factorization of the marginal. So we say that P of X is the sum of P of X given J into the a priori probability of J. This will have to do for all J in a discrete case, and if it's a continuous case, then we have an integral out here. And because of the commutativity of multiplication, we can interchange the order here in multiplication. And the interesting part is if we do a color combination between the two, we get the physical significance directly. Okay, so this is the a priori probability of the jth class or the jth model or the jth Gaussian. If we compare, we have a one-to-one, but then we'll also try to justify it in a mathematical manner. So pi j up till now, what we have got is this is the prior probability of picking the jth component of the jth Gaussian. And by taking a one-to-one between this conditional probability and the Gaussian, we see a one-to-one relationship. But what about the posterior probability that is given a particular point? What is the probability that this actually came from the jth Gaussian? This is an interesting problem. This is what is called mathematicians call it the responsibility. And this again comes from Bayes rule. That is, how much is the jth Gaussian or the jth model responsible for getting this point? So this comes from the Bayes rule. It's very simple enough, commutativity of multiplication. So the final function here is called gamma of j of x. This is called the responsibility. It is given by the Bayes rule. Okay, so we'll take a little mathematical break at this particular point, and we'll also realize that the question essentially is, what was Bayes by profession? The interesting thing is Bayes was actually a priest. Okay, because over time, men of God or people of God have actually been responsible for some of the most fundamental discoveries in mathematics and science in general. So Bayes was actually the Reverend Thomas Bayes. He was a priest. Then we all know about Gregor Johann Mendel. Who was this? The laws of heredity. Genetics started with the work of this Austrian priest. And then in more modern times, you'd have heard about this gentleman, Mahan Mitra, or sometimes also called Mahan Maharaj or Swami Vidyanathananda. He is one of India's best known mathematicians. And he does mathematics for a hobby. He's a monk of the Ramakrishna Mission order. He just does mathematics for a hobby. If you look up he's on the faculty of the Tata Institute of Fundamental Research. Remember Professor Ojha was talking about a very famous mathematician from TIFR. He's from, Professor Mahan Mitra is from the same organization. It's just that he does mathematics for a hobby. He's also an adjunct faculty at IIT Bombay. And he's won the 2011 Shanti Swarup Bhatnagar Award in Mathematical Sciences, which is the highest award for any scientist or engineer in India. He's also got the 2015 Infosys Prize in the Mathematical Sciences. Okay, so what we are trying to do is, or what I'm trying to say is essentially the fact that we engineers have a healthy respect for mathematicians, or in general for priests in that sense. And as an aside, what we are trying to do is we are trying to get the physical significance of the linear combination coefficients. So as before, we started with a little bit of a filmy touch. We saw Disney cars, right? We saw Lightning McQueen. Then after that, we saw the movie, the good, the bad, and the ugly. Here, what we are interested in is the life of pi. Okay? Yeah. In fact, the roles of pi and the tiger here, Richard Parker, are sort of inverted. Okay. In this case, we have to show that pi essentially is a probability. It lies between 0 and 1, and the sum of all of this is 1. How do we show it? This thankfully turns out to be an easy job because one can take an integral across both sides. So what is the integral of p of x? This integral will come up to 1. If we take an integral on the right hand side, we'll assume that we have nice and well-behaved functions, which are typically not Dirac deltas or what are called generalized functions, but good or well-behaved ordinary functions. So we can take the integral inside the summation. So we can interchange the order of integration, derivatives, summations, so on and so forth. Now pi j is a constant. So in that sense, we can also move the integral inside a bit more. So if we move the integral inside a bit more, I've got an integral over a Gaussian. So what is the area under a Gaussian curve? It's always 1. So we can get this expression, sigma pi j equal to So whatever we call jugaad, next time let's not call it jugaad, let's call it an engineering approach. Okay, so our jugaad actually proved to be correct. Okay, there's this nice example from Bishop's textbook wherein what is the intuition here? The intuition here is that there are three classes. There's the red Gaussian, there's the green Gaussian, and there's a blue Gaussian, and points have been sampled from that. However, this is an ideal situation. What is given to us is just this drab. What is given to us is this drab set of points. What we are supposed to do is essentially try to estimate. We have to try to estimate what Gaussian a particular point came from. So essentially, we have to start finding what are the responsibilities. This is the idea. Okay, so points could build points here. So why do I consider this to be a very nice example? I consider this to be a very nice example because, see, the color of a point, almost any color can be found out of RGB coordinates. Okay, so suppose we have normalized RGB coordinates, red, green, and blue. So what do we estimate the RGB coordinates of, let's say, a point here to be? We expect them to be closer to 100, RG and B. Points here, we expect them to be closer to 010. And what about points here? We expect them to be closer to 001. Okay, and here we try to find a number between 0 and 1 in terms of the R, G, and B coordinates, which will represent a particular color. So this essentially is the set of responsibilities. So we have the responsibility that a particular point came from the red cluster, responsibility that it came from the green cluster, and the responsibility that it came from the blue cluster. How will we compute that? This is something that is computed according to the expectation maximization algorithm, which we will see soon. Now let's look at the basic mathematical problem. The basic mathematical problem is here is that given a set of samples, okay, this is the basic philosophy. If we know the distribution beforehand, we can draw a set of samples from it. And we can also go vice versa. Given a set of samples, we can get an idea about the probability mass function. How do we do that? This is typically a histogram in d dimensions. So with this, we can generate samples according to any distribution. A Gaussian, for instance, we can do this in closed form. It's called the Box-Muller transform. So there's this sigmoid function, one plugs it into a uniform number generator, and one has a closed form distribution. One has a closed form formula to get a set of points which are according to the Gaussian distribution. And we can approximate it for any general distribution also, because we know that we can form a cumulative distribution function and then have a uniform random number generator generating a random number on the y-axis. We make it hit the curve and then we transform that to the x-axis. So whatever is on the x-axis will be generated according to any distribution. Okay. Now let's look at one-dimensional parameter estimation. What is given? We are essentially given a set of capital N observations. Okay, these are scalars, one-dimensional, and our model in this case is a one-dimensional Gaussian. One-dimensional Gaussian. So these are the N points which have come according to any physical process. What is our model? Our model is one-dimensional Gaussian. How do we characterize Gaussian? The mean vector and the covariance matrix. In this case, the mean vector is the mean, a scalar, and instead of the covariance matrix, we have the variance, or for that matter, the standard deviation. Either one of them is fine. What assumptions do we make? One of the assumptions that we make is that data points are IID. Well, I admit that because of my employer, I must say that I always have a nagging tendency to put a small t out here, IITD, but that's not really correct. IID stands for independent and identically distributed. Why is independence good for us engineers? Independence essentially is good for us lazy people, lazy engineers, because it allows us to multiply two probabilities without considering any conditional dependence terms. Okay, because what does the Bayes rule tell us? The Bayes rule tells us that probability of A into probability of B is, sorry, the probability of A and B is the probability of A into the probability of B given A. Now, only if we assume independence can we say that that is equal to the probability of A into the probability of B. And what does identically distributed mean? Identically distributed simply means that all of these come from the same model. All our points come from the same model. What is that model? Our model in this case is one D-dimensional Gaussian. How would we do it? So look at this. This is what mathematicians call a likelihood. That is, given our model, what is the model? Our model is one dimensional Gaussian. So we have mu and sigma square as the two parameters. So if our model is good, then we can use our model to generate back the same set of capital N points which we had observed, or rather which Mother Nature had given to us. So this is the likelihood, and our job at hand is to maximize this likelihood. So it's at least one of the things we should be able to convince ourselves as being reasonable is the fact that we should be able to maximize this likelihood, that is, maximize the chance. So if our model is good, the chances of it being able to generate the same set of endpoints which were given to us by Mother Nature, or which we had taken as observations from a physical process, that would be almost the same. So at least it is reasonable. Now, all of us who are mathematically inclined would also know that, well, this is something, this is not really completely optimal. Why is this not really completely optimal? Because if something has to be completely optimal in terms of probability, it must satisfy the Bayes rule. So what is optimum? The optimal estimation is essentially maximum a posteriori estimation, or the map estimate. So in this case, what do we have in the map estimate? We also have a priori probability, and we need to modulate our probability term with this a priori probability. However, there may be cases where it may not be possible to estimate this a priori probability. Okay, it may not be possible to estimate this a priori probability. For instance, what is the a priori probability of the moon coming and hitting the earth? It's not something that we can estimate, and it's also not something that we can assume to be a constant so that we can factor it out and somehow get that expression. We don't know anything about it. So in the absence of all of this, we have to take recourse to MLE, or maximum likelihood estimation. It's simpler, and in many cases there are other sort of methods to ensure that we will at least get a reasonable or a decent solution. Okay, things like we have constraint optimization. We will subject this to either one constraint or a set of constraints, and then go about it. For instance, maximum likelihood often tends to overfit data. So how do we get rid of that overfitting? We get rid of it by using regularization. We typically have a regularization term. So the first thing that we need to convince ourselves is that maximum likelihood estimation indeed is reasonable. Okay, and as per our formula, this is it. So this is independent and identically distributed. Independent means we can simply close our eyes and multiply these probabilities. Identically distributed means every point is coming from the same distribution, from the same model, which is one-dimensional Gaussian. Now, to maximize this is not very easy. So what we do is we take an equivalent problem. This is not the same problem, but is equivalent. We maximize, instead of the likelihood, we maximize the log of the likelihood. Why? We have John Napier to blame for this. Because see, log of x, if x is increasing, it is, okay, then log of x is also increasing. So the idea is that it has the same nature. Okay, and plus log has the additional advantage that it converts multiplications into additions and divisions into subtractions. Okay, this is interesting. So this is John Napier. So we have to blame him for inventing logarithms. This is the other gentleman who's involved in the history of logarithms. This is Euler. And in fact, Euler is interesting because log to the base E is named in honor of Leonhard Euler. And in fact, Euler is rather interesting because he's one person who's responsible for not one but two fundamental constants in mathematical physics. One is logarithms. Then my friends from the physics department also tell me something with regard to optics. There's a scattering constant or something like that. That's also called Euler's constant. It's called lambda. Well, the other interesting thing is in the year 2009, I got an opportunity to visit a university in Edinburgh. This is the Edinburgh Napier University, which is named in honor of John Napier, the inventor of logarithms. So there is this ultra modern glass and steel structure, and suddenly in the middle of it, there is a 16th century structure, a castle called Murchiston Castle, and the Dean International Relations sits in what used to be Napier's kitchen. So it gives a new sort of interpretation to Napier's bones, for instance. Okay, all right. So how do we maximize this log likelihood? The way to do this is we take a partial derivative with respect to every parameter that is involved. This is what variational calculus tells us. And what is a very simple way of finding whether one of the extrema is the maximum or the minimum? We simply put it back into the original function and then look in a small neighborhood around that particular extrema. So if that point is larger than the values in the neighborhood, then it is a maximum. If it is less, then it is a minimum. It's a very easy check. Well, in a sense, this is slightly less cumbersome than taking a second derivative test, then looking for higher orders, so on and so forth. So we take a partial derivative with respect to both of these parameters, set them equal to 0, and we reorganize these terms. And then the expression that we get out of this is actually something that should not shock us completely. So what does this tell us? This tells us that the maximum likelihood estimate of the mean is nothing but the sample mean itself. So sum the points up and then divide by n. And similarly, if we take a partial derivative with respect to the second parameter, sigma square, set it equal to 0, and reorganize these terms. So what we end up with, slightly messy expression, but then what we end up with is essentially saying that the maximum likelihood estimate of the variance is nothing but the sample variance, which is also not unexpected because all those of us who have fitted a Gaussian to a set of points, how did we do that fit? We would essentially take the sample mean and plonk the Gaussian there at that sample mean. And what do we take as the sample variance? Remember, the variance is the width of the Gaussian and also the height. Okay, because the area under the Gaussian curve has to be 1. What do we take it to be? We take it to be 99.97% of a Gaussian falls within the plus minus 3 sigma. Okay, so that is the that is a measure of how wide or how tall the Gaussian is. So we know where to place the Gaussian, which is the mean. We know how fat or flat or tall or thin the Gaussian would be in terms of getting its variance. So this is essentially it. Okay, now in the more general case, we have k of these d-dimensional Gaussians. All right, and in this case also, I'll quickly run through this set of slides because I know I'm also running a bit short of time. It's already 4 o'clock and I have some 45 minutes more to allow some time for questions. Okay, so here again, we'll make the same assumption and we will take the log likelihood and we would try to maximize the log of the likelihood. And here again, we will go ahead with variational calculus, and are the results that are going to come are actually again expected. They're expected because in a way, look carefully at this. What is this? This is the probability weighted mean. Look at this expression. What is what is gamma j? Gamma j was the responsibility. Do you remember that probability? It was the probability of the jth model, which was, or the jth Gaussian, which was accounting for that particular point. So this is nothing but an expected value. All right. This is an expected value, which is something that we knew. And similarly, we have our estimate of the covariance matrix. And there's a bit of a mathematical oddity here. And in this case, what we do is a bit of theory by Lagrange. And that little bit of theory is interesting. We'll come to it if time permits. Okay. But there's a easy way out. Okay. There's a little bit of a story also here that is involved, which is essentially constrained optimization, which is actually the creation of the mathematician of Italian origin who was in Paris at that particular point in time, Lagrange. Okay, he gave some very interesting theory for this, and that's the interesting part. Well, there is a little bit of theory because he was Fourier's teacher, and being as any self-respecting teacher, he never allowed Fourier to get credit for his amazing discovery. Why? For the simple reason that Fourier could not characterize his results mathematically. It was only after Dirichlet came up with his set of three conditions, and that was almost towards the end of Fourier's life, that he finally started getting recognition for whatever his theory was. Now, Lagrange was a very smart mathematician, and in fact, in machine learning, if you later go on to support vector machines, you would come across what are called the Karush-Kuhn-Tucker conditions, the KKT conditions. So there, the interesting thing is these are actually based on Lagrange's theory. So Lagrange's method of undetermined multipliers also extends to inequalities. This is the interesting part. And the KKT conditions are actually an embodiment of the sort of theory that Lagrange had extended for equations to inequations as well. Okay, so if we look at the basic problem of expectation maximization for Gaussian mixtures, okay, what we are looking at is we are given a set of n observations. So this is the very basic EM framework, or the expectation maximization framework. What is the model? Our model in this case is a mixture of Gaussians. Okay, we have independent and identically distributed set of points, mixture of Gaussians. So the mixture of Gaussians is, we have our set of a priori probabilities, which are our pi j values, and a vector which has all of these together is the pi vector. Okay, then we have the set of means. Okay, if we get them all together in a vector, we get, so essentially we get a matrix overall, that is mu. And then we have a tensor. We have a matrix of matrices, the set of covariance matrices. Okay, that's it. So this is our model. What are the parameters? We have three sets of parameters. Our sets of parameters are mu, sigma, and pi. Okay, so we know the basic expectation maximization philosophy. Okay, so we have some initialization for our three sets of parameters. We'll come to what might be a good initialization. And we initialize the value of the log of the likelihood. This is interesting because see, the log likelihood, given the log likelihood, we have a highly nonlinear formula for the log likelihood. So to obtain the set of parameters, that is the mu j's, the pi j's, and the sigma j's from the log likelihood, it's not possible to get it in an analytical form. So one goes the other way around. One adopts an iterative approach. One initializes the parameters and then finds the log likelihood from there. What is the expectation? The E step, one evaluates the set of responsibilities according to the current values of the parameters. Okay, according to pi j, mu j, and sigma j, all of these, one is able to evaluate the right hand side and get the corresponding. What are these? These are the responsibilities using the current parameter values. The second step is the maximization, where we re-estimate the parameters using the current values of the responsibilities. Okay, so we just define this particular term, and in the estimation, all of these formulae are actually whatever we had derived earlier. Okay, we had just derived them a couple of slides back. So this is the same derivation. So we have the probability weighted mean. This is the expected value. Okay, for mu j. Then we have a probability weighted value for the covariance structure as well. And we have a new estimate for pi j as well. After that, we evaluate the log of the likelihood, okay, using this, and we check for convergence. How do we check for convergence? We look at the value of the log of the likelihood. If this is the same as what it was in the previous iteration or very similar within practical bounds, then we say that, well, the algorithm has converged. An alternate way to look at this is not to look at the value of the function, the log of the likelihood, but to look at the parameters themselves. So if the values of the parameters do not change drastically across iterations, then it means that we have achieved convergence. Okay, so this is the expectation maximization algorithm for Gaussian mixtures. It's interesting. This also extends. Otherwise, this extends to a more general case as well. So why are we besotted with Gaussians? We are besotted with Gaussians because, well, a Gaussian is a nice curve. It is based on an exponential. So an exponential, you perform an integral, you still get an exponential. The same function back, you differentiate it, you still get a exponential. So it's called the God function. It's unchanging. And a Gaussian is based on that. And additionally, electrical engineers seem to love Gaussians for another reason. That is because a Gaussian is one of the only two functions which is unaffected by the Fourier transform. That is, feed in a tall and a thin Gaussian, the result in the Fourier domain, this will be a fat and a flat Gaussian, and vice versa. Feed in a fat and a flat Gaussian, you get a tall and a thin Gaussian. Okay, so that is one reason. And sometimes, like, tell an electrical engineer this assumption is Gaussian, and one can almost be sure that the electrical engineer would be convinced with his or her eyes closed. Okay, this noise model, it's a Gaussian. The electrical engineer will be perfectly satisfied. Okay, it's actually something like, yeah, it's a very smooth curve. It's a bell-shaped curve, but the actual reason, the only reason why it's often used, for instance, if you have studied image processing, you might have studied something called optimal thresholding, wherein is typically we are looking at a bi-level image or something close to a bi-level image. We assume a bimodal distribution, and we want to find one threshold which will sort of differentiate between the two distributions for the foreground and the background. Now one tries to fit a Gaussian there. Believe me, this is one of the worst fits for a Gaussian. It is sometimes more apt to have some other distribution like the Rayleigh Jeans distribution, a heavy tail distribution, which can model this better. But then why do we use a Gaussian? It's very simple. Okay, it's simple because it's just got two parameters. It is analytically nice, and for cases which we cannot handle analytically, we have our log tables which have values for the normal distribution. So people have sat and computed these values anyway. Okay, so Gaussian is nice. In fact, there was that internet meme a couple of years back, which is something like the HR of a company tells its employees during the sort of period where the industry is not doing too well, during the slowdown period, the HR tells employees that this month's salary is going to be paid according to a Gaussian curve. Okay, so people are amazed and people cannot understand. So when they ask, what do you mean? They say that a Gaussian is that bell-shaped curve. So that is essentially what you'll get in your salary, right? Ghanta milega. Okay. All right. So much so about Gaussian mixtures. So at this point, let us go to the let us see an illustration. In this case, if you look at a two-dimensional Gaussian from the top, and if the variance in both the dimensions is the same, then we are going to see a circle. So this is an initialization. In this case, once again, we have a red Gaussian and a blue Gaussian. So what is the first step? We compute the responsibilities. Now do you see almost a one-to-one correspondence with the version of the k-means algorithm that we took? There we were coloring the points either red or blue. In this case, it is basically a shade of blue and a shade of red. And what determines that shade? It is basically the value of the responsibility. All right. The second one, we recompute the parameters. Then this is the second iteration, the fifth iteration, and by the 20th iteration, we have converged. So the idea here also is that this is also provably convergent. But then once again, this can converge to a local optimum. Okay, and there's an interesting point. How do we make an initialization? We can make an initialization by running a complete loop of k-means before this. That is, we run k-means on the set of points, use that run of the k-means to initialize the respective sample means for the two clusters, get the sample covariances as an estimate, as the initial estimate, starting estimate for the overall covariance structure. And how do we get the pi j's? It's simply the relative number of points in a particular cluster. So we have a good initialization for using the expectation maximization for Gaussian mixtures here. Now for the last part of my talk, which is perhaps this particular algorithm is the Stauffer and Grimson background subtraction algorithm for videos. And this particular algorithm is, although it's about 2 decades old, but then often some of the state of the art in background subtraction is still based on, some of the practical state of the art in background subtraction is still based on Gaussian mixtures. The idea is, our modeling philosophy once again is that the color or the gray value at a particular pixel is given by a distribution, and that distribution is modeled as a mixture of adaptive Gaussians. Okay, so if X is a color in, let's say, in RGB space, so X is a 3x1 vector, we model this as a mixture of Gaussians. Okay, so if we have a color image, so X is a vector. It's a vector of RGB values, or it could be gray values. Okay, so just like we are trying to give a filmy touch to most things in this particular lecture, we will call it 50 shades of gray. Well, not 50, but about 5 times that number, because 8 bits or 1 byte results in 256 gray levels. So we get a unsigned char, we get a number between 0 and 255. And empirically, K, how do we estimate K? Empirically, K can be estimated to be a number between 3 and 5. This is typically done to limit the complexity. I'll give an example. So suppose we want to do background estimation for, let's say there's a camera which is looking at the sea. The camera is placed at the seashore and it's looking at the sea. So most of the times, let's look at it from the point of view of a pixel. So most of the times, it's going to it's looking at the water, right? And water is expected to be dark in color. So in terms of a gray level, so quite a lot of the times there'll be a peak around the low gray values. So there'll be a peak around, let's say, gray values of 10 or 20 or so on and so forth. So there's a peak there. So I can plonk one scaled Gaussian to sit there. Then it's not that all the time this water will be dark in terms of the gray level. So there could be a wave that comes and breaks. So if that wave comes and breaks, there'll be a bit of the splash, and that has a higher gray level, let's say. So we might see another mode of the distribution, let's say around let's say 127 or so, which is relatively bright. And under certain circumstances, there could be a specular reflection of the sunlight coming in and reflecting off the surface of the water. And that could be a very bright, blinding light. So I could have another peak around, well, something around, let's say 240 or 250 or so. So in this case, how have we modeled the color, or how have we modeled the gray value of the water? We have represented it with a mixture of 3 Gaussians. So K is 3 in this case. So this is typically done empirically, and this is done to restrict the complexity of the algorithm. We are looking at mixtures, which says that multiple entities can appear. For instance, somebody can come and stand in front of the camera. Okay, so the idea there would be that if the person again moves off quickly, then he or she essentially is a part of the foreground. However, if he or she just stands there, then his color gradually becomes a part of the background. That's the idea. In fact, some people also call it, it's in fact a part of ancient Indian philosophy. See the difference between what ancient Indian philosophers called the Jad and the Chetan. The Jad is the unchanging part, and the Chetan is the changing part. And in fact, electrical engineers like to call it the Fourier way to look at life. So essentially, with Jad, one has the unchanging or the very slowly changing set of entities. And Chetan is what changes very rapidly. So so when one essentially looks at the foreground is expected to be the changing part, and the background is expected to be the either the slowly changing or the unchanging part. Well, if one is given a video, one can say that the background, I can simply take 2 frames and take a difference, and whatever is the change in that difference, frame difference, that is the foreground, the rest is the background. Or, well, if you're familiar with digital logic, then one can say that one can do a XOR between these. So, well and good. But then this does not capture things which are varying slowly. Okay, things like there could be the leaves of a tree in the background which are swaying slightly in the breeze, or there is a flag that is fluttering, or let's say there's a river which is flowing slowly. So those are supposed to be background entities. So they have to be modeled with a background. So a simple frame subtraction or an XOR is not going to work. We have to have something a bit more sophisticated. And this is perhaps one of the best illustrations of an online variant of K-means, or and a mixture of Gaussian modeling. Okay, we'll look at it. This is also an adaptive algorithm. That is, it should adapt, it should change with different lighting conditions. And here, one can also initialize the mixture of Gaussians. One of the things that Stauffer and Grimson recommend is initializing the Gaussians with, let's say we take the first 100 frames of the video, the first tau frames of the video as history. And we say that we treat these first 100 frames as being representative of the entire video. So whatever is the distribution, whatever is the characteristic or the statistics in these first 100 frames, that extends to the rest of the video as well. So this is not supervised learning. This is not the ground truth. This is not training data. This is simply initialization. Okay, and we use a heuristic at a pixel to decide which one of the Gaussians would correspond to the background. So typically out of K, we will always, when we see the details of this algorithm, we will always maintain these, we will also always maintain a sorted list of Gaussians. So among the total of K Gaussians, which represent the background, we will use the first B in order to characterize the background. So if a pixel falls within the first B, in quote unquote important Gaussians, it's a part of the background. Otherwise, it's a part of the foreground. How is this adaptive? So let's say a person walks in front of the camera. So there, the gray level at a pixel corresponding to his or her set of clothes is going to be, initially it is going to be a part of the foreground, but then gradually if he or she doesn't move too much, it will start getting absorbed into the first B of those K Gaussians, and it will become a part of the background. Okay, so we have a heuristic at a pixel to decide which one of the Gaussians is most likely to contribute to the background. And pixels which do not match any of the background Gaussians would be the foreground. And foreground pixels on the other hand, could be grouped according to either a simple 2D connected components sort of algorithm, that is a linear time algorithm. It's a 2-pass connected components algorithm, or one could also use a 2-dimensional variant of k-means. Okay, if I've been talking too much, I think it may be nice if I first show a couple of examples. Let me try to show you a couple of examples. We'll start with a video. Please, can you unmute? Can somebody unmute his or her microphone and say whether this particular video is visible on the screen or not?
The video is visible, but
Okay.
there is no audio.
Yeah, there's no audio. Okay. Right. Yeah, there is a video which is visible. Let me try to get this a bit larger if possible. Okay. What can you see in this video? This video has been taken by a surveillance camera, and this video will loop around. The idea, this has been taken from a parking lot, and there is this black SUV which is backing out of the parking lot. Okay, there is a specular reflection which comes on the hood of the car and also on the top, and this car backs out of the parking lot, black SUV, and then goes off. And then there was a bit of breeze that day also, so the leaves of this tree are also swaying in the wind slightly. It may not be visible at this particular resolution. Well, so what does intuition tell us? Intuition tells us that this should be a part of the background. Okay, the leaves of the trees are swaying slightly, and of course, what else is moving? There are these two loafers who are roaming about the parking lot without a care in the world, or without a job. And one of these loafers you may be able to recognize, this particular loafer in a blue shirt and dark gray trousers. Yeah, that's me. Okay, so in this case, the idea is, given this video, one is supposed to, the problem at hand is to estimate the foreground and estimate the background and do it adaptively. So in this case, so how would we do it? So the foreground would be things like this black SUV. See, we cannot segment the black SUV because this is not uniform in color. And see, there are specular reflections. There are different, literally shades of gray, plus this also goes into the shadow region. Okay, then these two loafers come and stop at a particular point, at which point we might be inclined to put them into the background, but then again, they should become a part of the foreground because they're making random Brownian motions all around the parking lot without a care in the world. Okay, let us go back to, so I was pretty excited when I first heard of this particular algorithm. And when I wanted to see how this algorithm operates, what did I do? I gave out an assignment. Okay, we are extremely lazy people. We are teachers. We don't do work ourselves. We get work done, right? And all of these results, I'll show a couple of these videos. These are results with different sets of parameters. And please believe me, if an IIT Delhi student, our students are notorious for being horrible at programming, at coding. For instance, it's also rumored that the term spaghetti coding would have started off from by people looking at code which had been generated by IIT Delhi students. So it turns out to be a pretty simple problem to code up, and people have taken different sets of parameters and generated different videos. Let's try to see some of them. So this, for instance, is, what is this? This is the background. This is the estimate. And here you can see that after a couple of frames, you'll see that the estimate of the background is pretty reasonable. That's one of the things that you should be able to see here. So when these two loafers stop at the point, they suddenly become part of the background, but then again they get absorbed into the background model. So when the video replays, please have a look. Initially, see, I'll just stop it here. Initially, everything is a part of the foreground here. Okay, but then look, gradually it's the algorithm starts adapting. Okay, the algorithm starts adapting, and gradually it builds up the background so that a little bit of the information about that black SUV still remained, but then gradually you'll see this algorithm adapting. So here, for instance, when the loafers stop, they suddenly become a part of the background, but then again, when they start moving, they become a part of the foreground. So this is the rest of the background. And now you can see that the evidence of that black SUV is nearly gone. And this is the complementary set of observations. So this is the foreground model. So you can see that, well, there are errors. There are some pixels which are erroneous. For instance, here that information simply isn't there. That black SUV comes into the shadow region. Okay, so you will see some pixels that are there in error, but then overall the algorithm has adapted itself relatively well. There would be pixel level errors, but then the algorithm is able to adapt itself relatively well. So whatever is in white is essentially a foreground pixel. So there are experiments with other parameter values. So here again, you'll see that when the algorithm started off, everything was the foreground here. Everything was the foreground. So it essentially started off with a white image, but then gradually it builds up the background model. And after a while, for instance, you'll see that this is with a different set of parameters. You'll see that the parking box also disappears because it is built, and then this part also disappears. So there are noises here and there. There is noise here and there, but then you'll see that it has gradually estimated the foreground. Anything that is black here is a part of the, is essentially the background. So you'll feel that gradually it has estimated the background relatively well. And we'll see the complementary information. The complementary information is the foreground. Okay, so whatever is white here is the background. So you'll see that it has estimated the foreground relatively well, which are the colored pixels. The rest of it is the background. So you'll see that occasional noise pixel come in, or whenever these two loafers are going within that shadow region and then coming out. Okay, but then overall, it has been able to estimate both the foreground and the background relatively well. We'll see some other examples. One of them is this. This is an experiment with a different set of parameters. So here again, this is the background model. Whatever is in color is the background model. So you'll see that it has been able to estimate the background relatively well. So the influence of the foreground object, which is that black SUV, is gone. And when these loafers turn, see, they've suddenly become a part of the background, but then gradually the background model will start updating itself as those two loafers start moving away. And it has been able to estimate the background relatively well. So complementary piece of information comes in estimating the foreground. Okay, so in this case, you'll see the foreground, and you'll see that as the algorithm progresses, it is able to estimate the background with a good deal of confidence. Okay, so these two loafers and their shadows. So this essentially is the foreground. So here you'll see some noisy pixels, but then they'll gradually disappear. Or some may still remain, but then fine, they can be removed by other methods. Then an experiment with another set of parameters. So here the frame number is also mentioned. So in this case, the colored part is the background, and whatever is in white is the foreground. Okay, so you can see some pixels which are in error, but then you'll also see that the algorithm adapts itself relatively well. So this is an experiment with another set of parameters. Then I'll show the video of complementary information. So complementary information is estimating the foreground. So whatever is in color, so you see the frame number mentioned here, and whatever is in color is essentially the foreground, and whatever is in white is the background. So you'll see some noisy pixels here and there, but then overall this algorithm works pretty well. It is quite robust. Okay, and that's it. With another set of parameters, there are people who are working on deep learning based foreground and background estimations as well. And I believe one of Santosh sir's close friends, Dr. Subramaniam, Morala at IIT Roped. He's also working on some part of this, if I remember correctly. Well, this is an estimate. This is a run with another set of parameters which shows the input video and the output video side by side. So what you see on the right hand side is essentially the background estimate. So gradually it has, the effect of the foreground has gone off. It will briefly come in when the two loafers stop. Yes. Okay, they become a part of the background, but then gradually they again blend. So gradually they blend into the foreground, and the background model by this time adapts itself in a rather robust manner. So you can see this as the video replays. So here the black SUV is moving off, and gradually it has been able to adapt itself. And so the black SUV information from there is still a part of the background, but then gradually that information disappears. So this is with a different set of parameters. And here they suddenly become a part of the background when they stop, and then they start moving again and they become a part of the foreground. Okay, I have,
Dr.
I have,
Roy, I have a question here.
yeah,
And this video is very interesting. In fact, I am also a faculty at one of the universities and wanted to do a project for a sort of self-driven car, but only this part where the car could reverse itself. Now, my question is, like here we have a shadow,
yeah,
tree's shadow,
yeah, yeah.
and we want the car to make a decision and know that this is a shadow and it's not a stationary object, it's not another car.
That's it's a very, very difficult problem. Shadow
No, I
removal.
don't think for you it won't be that
No,
difficult.
madam, it's Dr. Kataria. This is actually a very, very difficult problem. And in fact, when we were kids, we were taught that how do you differentiate between a person and a ghost? How do you do that? At least in the villages, what was taught to little children was that the ghost is not going to have a shadow. Okay, but yeah, jokes apart, this is actually a very difficult problem, because in this case there is nothing which indicates what a shadow really is. The shadow could actually be a person, it could be another moving object also. However, there has been some work in trying to detect and eliminate shadows. For instance, okay, there is one lady who has raised her hand, Monisha. So please just unmute your microphone and speak. Okay, anybody, please unmute your microphone and speak. There are some rather interesting heuristics which can actually be used to estimate shadows. And